Hi. So this is the next question. And this question is a little different. We have a linear system, and then we also given an initial condition. So it's an initial value problem. Now we want to find the particular solution of this initial value problem. So you know that the very first thing we want to do is we want to find the general solution first. Now after finding the general solution, then we would now implement the initial condition that we're given in the general solution so that we can find a particular solution that satisfies both the differential equation and the initial condition that we're given. So let's start by finding the general solution of the linear homogeneous system that we're given before we move to the next step. Now the next thing you do is you find the eigenvalues of A. Now A minus lambda I is the same thing as the determinant of the matrix obtained from here after you have deducted lambda from all the diagonals. So 1 minus lambda, you have 2 minus lambda, you have 1 minus lambda. So you have 1, you have 4, 0, 0. So you have 1, you have 1. Now this equals, it says it equals 0. So by the time we find the determinant of this whole matrix, what we would obtain is lambda cube minus 4 lambda squared. I hope my calculator is not failing me here. Plus lambda plus 6 equals 0. Now when we solve this cubic equation, what we obtain is we obtain lambda 1 equals -1, we obtain lambda 2 equals 2, and then we also obtain lambda 3 equals 3. So this is what we obtain. Now what you observe here is all the eigenvalues we've obtained here, they are all distinct. So we have distinct eigenvalues. They are not equal at all to each other. So since we have distinct eigenvalues, now that implies that the kind of solution we should be expecting should be of this form: C1 K1 e to the power lambda 1t plus C2 K2 e to the power lambda 2t, and plus C3 K3 e to the power lambda 3t. So where lambda 1 is the eigenvalue and K1 is, where lambda 1 is what we have here, and K1 is the eigenvalue that corresponds to lambda 1, K2 is the eigenvalue that corresponds to lambda 2, and K3 is the eigenvector that corresponds to lambda 3, K2 is the eigenvector that corresponds to lambda 2, and K1 is the eigenvector that corresponds to lambda 1. So we're going to go ahead, since we know that to find the general solution, I need to find, we've already gotten K1, we've gotten lambda 1, 2, and 3, so we need to find K1, K2, and K3. So that's the next step, to find the eigenvector that corresponds to each of these eigenvalues. So we solve A minus lambda I x equals 0. So I'm going to start with the first eigenvalue, that is for lambda equals -1. So for lambda 1 equals -1, so A minus lambda I x equals, we have 2, 1, 4, 0, 3, 0, and then you have 1, 1, 2 times x, y, z equals 0, 0, 0. So to solve this system, we will reduce this matrix like we have been doing before. When we will reduce the matrix, we have 1, 0, 2, 0, 1, 0, then you have 0, 0, 0 times x, y, z equals 0, 0, 0. Now to complete this whole process, we rewrite this in equation format, so that's 1 times x, which is x, plus 2 times z, so that's 2z equals 0, and then for the bottom we have y equals 0. So the free variable is here is z, so we're going to set, to find the basis of that, we're going to set z equals 1, and then if z is 1, I can find my x. My x is going to be -2z, which is -2, and my y is already given to be 0. So I've been able to find my K1 to be x, y, and z. So the next thing is to find the eigenvector that corresponds to the next eigenvalue here, which is lambda 2 equals 2. So now for lambda 2 equals 2, to find the eigenvector, I'm going to solve a minus lambda I x equals 0. That is, what I want to solve is, so a minus lambda I is just deducting lambda from all the diagonal entries, and then what we have there is negative 1, 1, 4, you have 0, 0, 0, you have 1, 1, negative 1, times x, y, z equals 0, 0, 0. So this is exactly what we have. And then to solve this linear system here, all we need to do is we reduce this, we row reduce this coefficient matrix here. When we row reduce the coefficient matrix, we have 1, 0, negative 5 all over 2, we have 0, 1, 3 all over 2, we have 0, 0, 0, here we have x, y, z, and this equals 0, 0, 0. So when we write this now in equation format, so 1 times x, that is x, 0 times y is 0, negative 5 over 2 times this, that's negative 5 all over 2z equals 0. Then for the bottom, we have y plus 3 all over 2z equals 0. Also, you observe that the free variable we have here is z. So the free variable is z. So we set z to be 1. So when we set z equals 1, our y equals negative 3 all over 2, and our x equals 5 all over 2. So having gotten this, I've been able to find my next eigenvector k2, which is going to be x, y, and z. But then because I don't want fractions here, so I could choose my k2 to be 5, I'll multiply all through by 2, negative 3, and 2. And that's for my k2. So the last eigenvector I want to find is the eigenvector that corresponds to lambda 3 equals 3. So to find that, so that's for lambda 3 equals 3. To find eigenvector, I'm going to solve a minus lambda I x equals 0. That is, what I want to solve is, in place of lambda, I want to solve a minus lambda I is going to be negative 2, 1, 4, 0, negative 1, 0, 1, 1, negative 2 times x, y, z equals 0, 0, 0. So this is what we have. And then to solve this system, all I need to do is to row reduce the coefficient matrix here. So when I row reduce that matrix, what I obtain is 1, 0, negative 2, you have 0, 1, 0, and then you have 0, 0, 0. This is what I obtain. You have x, you have y, you have z equals 0, 0, 0. And at this stage, you might want to write this whole thing in equation form. So that's 1 times x, which is going to give me x minus 2z equals 0, and 1 times y equals 0. Also, you'd observe here that the free variable is always z. It is z here again. So since the free variable is z, to find the basis of this system here, the basis of the solution space of the system, we set z to be equal to 1. So if z equals, when z is 1, our x is 2, while our y is just 0 as given here. So from there, we have been able to find k3 to be 2, 0, 2, 0, 1. So we have k3 to be 2, 0, 1. We have k2 to be this 5, negative 3, 2, and then we have k1 to be negative 2, 0, 1. So, and then we said this is what our general solution should look like. So I'm going to go ahead and write that. So therefore, we said our x should be c1 k1 e to the power lambda 1t plus c2 k2 e to the power lambda 2t plus c3 k3 e to the power lambda 3t. That's going to be c1 into k1. So the k1 we obtained above was negative 201 e to the power, and we said this corresponds to negative 1, that's the eigenvalue negative 1, plus c2 into the k2 we obtained above was 5 negative 3 2, like I showed you above, and we said it corresponds to the eigenvalue 2, that's e to the power 2t, plus c3 into k3. So our k3 is 201 e to the power, it corresponds to, as this one corresponds to the eigenvalue 3. Yeah, I almost forgot that. E to the power 3, e to the power 3t. So that's what we have for the general solution. And then if, according to what we're given, now this is the general solution um, of the linear homogeneous system. But then the question does not stop there. The question says, of all the solutions, find the one that satisfies this initial condition. Now what this one says is, it says this is t. So it says when t equals 0, x of t equals 130. That's what I want to do now. So this is my x of t. My x of t is this. So when t equals 0, so x of 0 now, x of 0 is just going to be c1 negative 201. So e to the power 0 is 1 plus c2 5 negative 32 e to the power 0. This is 0, so it goes to 1 plus c3 201. So e to the power 3 times 0 is 0, so that also goes to 1. So we are told that this x of 0 equals 130. So it equals 130 there. Equals 130. So when you write this, this is going to be that's going to be a c1. Let me write that. Well, a c1 times negative 2. That is negative 2 c1 plus 5c2, then plus 2c3. This equals 1. Then c1 times 0 is 0. Then negative 3c2. Then c3 times 0 is 0. Then this equals 3. And also c1 times 1 is c1 plus 2c2. Then plus c3 equals 0. So we want to solve this. And by the time we solve this, when we punch our calculator, we're going to have c1 to be equal to negative half, c2 equals negative 1, and while our c3 equals 5 all over 2. So we have been able to find c1, c2, and c3. So I'm going to substitute this c1, c2, and c3 into this place here. So we do not have arbitrary constants in our solution anymore. So therefore, the particular solution, let me say the particular solution of the system is given by x equals, so we are replacing c1 now with negative half, so that'll be negative half into minus 201, where is it? Yeah, minus 201, then e to the power negative t, then minus 1 into 5 negative 32 e to the power 2t, then plus 5 all over 2 into 201 e to the power 3t. Now this that we have here is a particular solution to the initial value problem that was posed initially.